These are two different types of solar cells. This is the current mainstream crystalline silicon solar cell. Silicon wafers are thin and prone to breakage, so they are sandwiched between glass and polymer like this. This one is a perovskite solar cell. Compared to the silicon type, it is quite thin and lightweight. Now, let's shine a light on it. You can see it generating electricity. It can generate electricity even when folded. The perovskite solar cell is the most important candidate for next-generation solar power generation. Japan has limited flat land, and at present, most large-scale solar power generation facilities are situated away from areas of energy demand. It is difficult to build large-scale solar power generating facilities in large cities. This is because conventional solar panels are bulky and dense, and installation sites are restricted. This is where perovskite solar cells provide a promising solution. Commercialization of lightweight, flexible solar panels would enable installation in challenging locations, such as the roofs of factories, gymnasiums, and agricultural greenhouses. We could expect an expansion of solar power generation in areas with high energy demand. Solar cells generate power using a semiconductor. A perovskite solar cell converts light to electricity using a compound with a perovskite-type crystal structure. Perovskite crystals are also semiconductors. They consist of organic substances, which are the materials that make up our bodies, lead, and substances called halogens, such as iodine. They use materials different from conventional silicon solar cells. When viewed in cross-section, the perovskite layer is centrally located, sandwiched between a semiconductor layer, electrodes, and a transparent conductive material. Because perovskite layers comprise numerous tiny crystals, they demonstrate significant resistance to bending and distortion. They can be produced by the solution coating of materials and layers, offering the potential for cost reduction through mass production. Increased commercialization could create new opportunities for Japanese industry. The supply chain for perovskite solar cells differs significantly from that of crystalline silicon solar cells. It mainly uses chemical products. Japanese manufacturers have a large global share of chemical products, so I believe that Japan can take the lead in the perovskite solar cells industry. The origins of perovskite solar cells date back to 1991, when Professor Michael Grätzel from Switzerland invented the dye-sensitized solar cell. In 2009, a group led by Professor Tsutomu Miyasaka from Toin University of Yokohama replaced the dye in dye-sensitized solar cells with perovskite, converting light to electricity for the first time in the world. In 2009, I was a lecturer at Toin University of Yokohama. Then, Henry Snaith, a professor at the University of Oxford, and I began joint research. However, as perovskite solar cells originally contained an electrolyte, and perovskite crystals can decompose due to the presence of electrolytes, this resulted in a low conversion efficiency of 3.8%. Therefore, we devised a method to convert the electrolyte into a solid. We applied the method we had been researching for solidifying electrolytes in dye-sensitive solar cells to perovskite solar cells. Even after moving to AIST, we continued our research, and in 2012, we attained a conversion efficiency of 11% with solid-state perovskite solar cells. Achieving the breakthrough of surpassing a 10% conversion efficiency instantly heightened the potential for practical application. This served as the catalyst for global research momentum into perovskite solar cells. Currently, at the research level, an efficiency of over 20% has been achieved, comparable to silicon solar cells. Practical applications are expected soon. Perovskite solar cells are attracting attention as a technology that could aid in achieving the goal of being carbon neutral by 2050. AIST is addressing three main issues as it moves towards its commercialization. Increasing durability. Develop technology that improves durability to achieve an increased cell life of 15 to 20 years. Reducing cost. Develop processes capable of mass production and highly efficient, highly durable cells. Increasing efficiency. Improve conversion efficiency and develop technology that evaluates performance using large area modules with high reproducibility. AIST's strength lies in its system, which facilitates comprehensive, integrated research encompassing the development of materials and process technologies, alongside analysis and evaluation. As a leader in the field of perovskite solar cells, numerous researchers are taking on the challenge. Development of materials for durability. We're working to improve durability. Perovskite crystals are naturally ionic, which makes them weak against water and humidity. Extended exposure to light also decreases their performance. It's therefore important to create highly durable materials and technologies able to maintain high conversion efficiency. As perovskite solar cells comprise a range of materials, we are exploring optimal conditions while elucidating interactions.
I am developing new charge transport materials, CTMs.
I'm developing new dopant materials for increased efficiency and durability. I'm researching new inorganic semiconductor materials that can be coated over perovskite. I'm working on a method called vacuum deposition for coating perovskite. Solar panels face challenges from rain and harsh sunlight, making improved durability a vital concern. That specific issue poses a valuable challenge. These researchers will continue to combine their respective skills to achieve durability that is equivalent to 15 to 20 years of practical use. Establishing an automated cell fabrication system. This is the only system of its kind in the world. This system is vital for advancing the development of materials needed to commercialize perovskite solar cells. The knowledge gained by AIST over the years has led to the development of the automated cell fabrication system. This is the first time in the world that cell fabrication has been successfully automated. All processes are automated, including cleaning the substrate electrodes, layering materials for the electron transport, perovskite and hole transport layers, as well as depositing the backside electrode to separate the cells. Generally, there is considerable variation in the performance of perovskite solar cells, necessitating the production and examination of numerous cells to adequately evaluate materials and processes. This system automates cell fabrication and eliminates human factors, reducing performance variation in the solar cells. The automated perovskite film coating system is an essential part of the automated cell fabrication system. Making a high-performance perovskite crystal film is so complicated that it requires exceptional skill. I realized that it was challenging to make the reproducible perovskite coating layer, so we started to develop an automated process. Automation allows individuals to reliably produce uniform products in film coating and drying processes. The automated cell fabrication system was developed by utilizing insights obtained from the establishment of the automated film coating system. Using this system, work efficiency was more than 10 times better than the previous system. Moreover, the ability to evaluate prototypes and durability under various conditions is expected to shorten R&D time and improve efficiency. In the future, we will link with AI to optimize conditions more efficiently. Establishing film coating technology suitable for mass production. With the automated perovskite film coating system, The Perovskite film is produced using the single wafer processing method. An ink solution is dropped onto a substrate, where a rotating centrifugal force produces a thin uniform film. The film is then dried to produce one wafer at a time. Also, high performance can be achieved by using solvent treatment to coat a smooth, uniform perovskite layer. Responding flexibly to changes in materials and production processes and making a variety of prototypes are major advantages in development. However, single wafer processing can only process an area of 30 centimeters in diameter at one time. Achieving commercialization will require cost reduction through mass production. Currently, we're developing technology for continuous coating of perovskite film to achieve mass production. This is the roll-to-roll method, in which coating and processing are carried out while conveying substrates in a film-like roll. Because the film is continuously rolled, a large volume of film can be coated simultaneously. With continuous coating, the solvent treatment process is impossible, which makes it very hard to produce a smooth, uniform coating. However, with the technology I developed, we have achieved high-quality perovskite film. In the future, I would like to contribute to the ability to process larger surface areas. The advantage of AIST is its integrated research capacity, from materials to solar cell modules undertaken by experts in each field. We will continue advancing technology development towards commercializing perovskite solar cells and strengthening the supply chain.